Hello everyone, I'm Emmanuel Raj, a senior machine learning engineer at Tieto. I'm currently based out of Finland, and it's my pleasure to present to you our work on Edge MLOps, an automation framework for AIoT applications. This work is done in collaboration with my colleagues and co-researchers, Dr. David Buffoni from Tieto, who's based in Sweden, Dr. Magnus Westerlund, who's from Arkada University of Applied Sciences and also is based in Finland, and Kimmo Ahola, a senior scientist from research organization VTT Finland based in Finland. And together, with this collaboration, we were able to derive an automation framework for AIoT applications, which we call Edge MLOps. Let's look at what this automation framework is about. So before we look into it, let's delve into the problem that we are addressing by looking into artificial intelligence of things and the problem itself, and then the solution to the problem, which is the Edge MLOps, the automation framework for AIoT applications. Thirdly, the experimental framework validation, where we apply the Edge MLOps framework to a real life use case. And fourthly, we will assess the reliability of the framework in a quantitative manner. So let's delve into it by looking into artificial intelligence of things and it's what it's about. So artificial intelligence of things is a combination of AI together with IoT infrastructure to achieve more efficient IoT operations and decision making. And in typical scenarios in AIoT setups, there are multiple IoT devices, sensors, and there are edge devices typically near these sensors to assist in computing, where we can deploy machine learning models to make some predictions or decisions based on the data coming off the IoT sensors. And we also can make use of cloud computing or cloud technologies available at our disposal. And all of these technologies can be infused using the 5G networks or 4G network capabilities. And in these kind of scenarios, the problem that we are addressing is of bringing the continual learning capabilities at the edge for machine learning models and really enabling the automation for it. And in order to address this problem, the question that we are trying to solve is how can we integrate all of these components into a framework that can orchestrate continuous integration and continuous deployment for machine learning models at the edge, and all of this using state of the art tools and methods. And uh, in order to address this problem, we have come up with a solution after multiple iterations on different problem contexts and problem setups. And today we will also discuss one of the problem setups or the use case that we have applied the framework to. But let's delve into the solution itself, which is the Edge MLOps, the automation framework for AIoT applications. So this is the framework itself, the Edge MLOps framework. It is highly modular. It comes in components. It's cloud agnostic. It is technology agnostic. It is tool agnostic. So it can be customized to multiple use cases, and you can take this framework and plug and play into your use case. So let's look into how this works. On the high level, there are two modules: the cloud orchestration layer and the edge inference layer. In the cloud orchestration layer, we are orchestrating the cloud applications in order to deploy the machine learning models continuously on the edge, and do the inference and get critical insights from it. So in order to do that, we have machine learning pipeline to train the machine learning models by ingesting the right data, training the machine learning models, evaluating the models, then packaging them into standardized formats such as containers, and then registering them on model registry, which is linked or stored in the central storage, which we have part of the cloud orchestration layer. And from this storage and model registry, we pick out the best models and use the CI/CD module, where we build artifacts out of these models to deploy and release them to be deployed in the edge devices. And we can use triggers to enable those releases, such as data driven triggers, schedule triggers, metric driven triggers. And also in the CI CD component, we manage the source code and do the data sanity tests, unit tests, integration tests, which are critical to drive CI CD operations and maintain the sanity of data and the deployments. And lastly, the fleet analytic component in the cloud orchestration layer, where we get a bird eye view of our operations in the edge and also on the cloud as well. So this is really the central place where we can see the decision making of model performance, the edge devices health, the cloud applications state, and so forth. So that's in a nutshell cloud orchestration layer, which orchestrates all the cloud applications to drive edge operations. And in the edge inference layer, we have all these edge devices set up in particular rooms or infrastructure, where we connect to the IoT sensors, and we enable continuous integration and stream the IoT data onto the edge devices. And this is typically the case where multiple edge devices can be set up. As you can see, one, two, three, and till n number of edge devices. It can scale, and the framework is completely automatable. And we will prove the functioning of the automation nature of this framework by using an experiment that we discuss in the next section. So let's jump right into the experiment itself. We applied this Edge MLOps framework on this setup, where we have a campus which has three meeting rooms where people meet to have meetings. And in these meetings, we have installed IoT sensors which monitor the room air quality, and we get data in different parameters such as temperature, humidity, air quality index, and so forth. And by having these sensors, we wanted to accumulate data and process this data, and apply probably machine learning to predict the room air quality in the coming 4 hours, for example. So we have these edge devices set up, one edge device set up in each room. So in room A, we have Raspberry Pi, room B, we have NVIDIA Jetson Nano 2, room 3, we have a Google TPU Edge. And here is where we deploy machine learning models on this edge device. And the idea is to enable continuous integration and deployment of models on these edge device and enable continuous learning. So in order to do that, we had to train models firstly. And in order to train the models, we had to collect the data. And the training data was accumulated over the timeline of 3 months, where we collected the data for each room. As you can see in the rooms column in the data, there are three different rooms that we collected data for. And the data volume is about 45 MB with 537873 number of rows on the whole. And the data consists of parameters such as the air quality index, ambient lighting, humidity, pressure, and temperature, with timestamps as well. So, in order to analyze this and see what trends are being there, we noticed when we plotted the time series that the data is non-stationary and there's high variance in the data for these three rooms. You can see the time series patterns in green, red, and blue color on the time series chart. And on the right side, we have the normal distribution for the air quality index of each rooms, as you can see in red, blue, and green color for respective rooms. And based on this data, we trained our machine learning models by implementing four different algorithms to do the multivariate time series forecasting to predict room air quality index for for the next 4 hours or 4 hours in advance. So we applied algorithms such as multiple linear regressor, extreme learning machines, which is a form of neural network, and random forest regressor, and support vector regressor. So on the right side in the table, these are the results of the model training. I'm going to use root mean square error as a metric to validate the model training results, and you can see the results of model training for all three rooms for each algorithm. So after the models are trained, we packaged them into containers and we registered them into the model store from where the model registry from where we can deploy the models. And we deployed the models in using Docker containers into the edge device. There are two different applications running inside a Docker container. One application is to continuously fetch the data from the IoT device, and we used MQTT protocol for that. And we performed machine learning inference, of course, using the machine learning model. And we cached some data temporarily that was sent to the cloud in a synchronous manner. And then the second application here monitors the model performance in terms of model drift as well. So when we look at the reliability of the automation framework, we before we delve into that, it's good to understand the data flow of the use case as well, of how we implemented the use case in terms of the cloud operations, edge operations, and IoT operations. In the cloud, we processed the data and did the model training. In the cloud, also, we stored the model and did the model selection to pick out the best model and deploy them on the edge, where we do the inference to predict anomalous behavior in terms of room air quality index. If the room air quality will be bad or good in the meeting rooms or not. If the room air quality prediction is suggested as bad, meaning that it's above 100 air quality index, then we would alert the guardian or the administrator of the system to take particular action to regulate the room air quality index in the room by taking actions such as opening the windows or for ventilation or regulating the air conditioner, these type of actions. So we also monitor the model drift using the ML model performing script inside the Docker container, which would suggest if the model is performing well or not. By well, we mean below the threshold, and by bad, we mean model drift is above the threshold. If it's above the threshold, then we retrain the model, and we call the predictive model recommender in the cloud to deploy another substitute model. And in this way, we were able to enable continuous delivery of models to the edge and also enable continuous learning as well using the retraining feature of the pipeline. And in the IoT part, we have the IoT sensors continuously streaming data to the model where we do the inference, and this is the data flow of the use case. And in order to facilitate this use case, we used the data flow. In order to facilitate the data flow, we used our Edge MLOps framework, and these are the components that we used. The cloud that was used was Azure, and we used Azure Machine Learning Service to orchestrate the machine learning pipeline, where we provision compute and storage needed to ingest the data to train the models and to store them in the blob storage, from where we pick out the models and deploy the models as we have seen previously inside the edge devices, and enable the continuous deployment in the edge inference layer on particular edge device, and enable the continuous deployment and delivery of the models, and in turn enabling the continual learning for the model. And we can see a bird eye view of the operations in the edge fleet analytics component, where we use Power BI and IoT Central applications from the Azure cloud to get a bird eye view of the operations in terms of edge device health, the model performance, and the system performance in general. So, in order to assess the reliability of the framework, we developed reliable fleet analytics process taxonomy, where we comprehensively gauge the reliability of the ML ops operations on the edge devices. So this taxonomy consists of three main parts. One where we analyze the analytics process, which is about modeling approaches, decision making, and automated accountability. And secondly, we gauge the system supervision in terms of statistics for the metrics that we are monitoring, such as the model drift, and also the alarms that are generated based on the model performance. And then thirdly, we also gauge the device analytics as well, where we monitor the device health using telemetry data, and we coordinate the devices in this section. And after a period of 45 days of experimenting and deploying the models continuously on the edge devices for the experiment, these are the visuals of the results. As you can see, these are three different rooms: room A10, room A29, and room A30, where we can see the yellow line is the predicted model predictions, and the blue line is the actual room air quality. So this is the performance of the models in three different rooms. So we have been continuously deploying models in these rooms, and these are the qualitative results from to gauge the reliability. So in the analytics process, we observed that in the 45 days of the experiment that we did to continuously deploy the models and to automate the process of continuous learning and continuous deployment of machine learning models on the edge, we noticed that 23 different models were deployed, and these deployments were driven by the model drift threshold that we set. And the 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 metric that we choose was root mean square error again, to compare the inputs for the model and the outputs. And if we would figure out if the root mean square error is above the threshold for this experiment, we choose the threshold 8. And if it's above the threshold, then we would deploy another model, a substitute model, and retrain the old model in order to enable the continual learning capability and do the continuous deployments as well. So 23 new models were deployed, and uh, the use case was supervised in terms of alerting the guardian when the guardian or the administrator of the system when the room air quality index was above 100, when it was predicted to be above 100 4 hours in advance. Then an alarm would go to the administrator and they would regulate the system. And when we looked at the device health and the performance, we monitored telemetry data such as accelerometer, gyroscope, humidity, magnetometer, pressure, and temperature. And during the course of the experiments, all edge devices performed without any failure, and we monitored costs, inference speed, and latency during this. And we did a head-to-head comparison of comparing the costs and the performance of 10 edge devices, doing inference on 10 edge devices versus doing inference on one cloud node. And we noticed that there is exponential difference, and we benchmarked with Raspberry Pi 4 as edge device versus data science to virtual machine on Azure. And while doing this, we noticed that the average cost of 10 devices, running 10 devices, Raspberry Pi for a month is around 10 euros, and the same for running one cloud node is around 93 euros per month. And if we scale this to 1,000 edge devices versus 100 nodes, we noticed that there's the cost of 1,000 euros per month versus 9,300 euros per month. And in the bigger picture, there's 9x cost reduction when we implement edge computing near the IoT devices versus doing the inference on the cloud, and the inference speed was 9 times faster when we implemented the inference on the edge devices. And we were able to also prune out the unnecessary data and save the storage space. And while doing the inference on the edge, we could avoid 2-second latency, which was evident on the cloud. And as part of the future work, we proposed this extension for federated learning, which takes in as a model as the input instead of data in the ingestion step. where we tune the hyperparameters and we can deploy these different models on different edge devices and scenarios in the edge inference layer. And as part of the future work, we have we will focus on making the Edge MLOps framework fault tolerant to test it end to end, do the smoke tests, unit tests, and integration tests, and also test the security and privacy aspects as well, and uh, check the robustness of the system more further. Thank you for your time, and thank you for listening to our presentation.